So in this lesson, we're going to tackle optimization. So it's really the last thing we need to sort of tackle. And we have done a little bit of optimization really mildly in our quadratics part of our units. We were looking at those sorts of functions. But we're going to take it to the next level here by introducing concepts of calculus as a way of figuring that kind of stuff out. So we're kind of pretty much up to here solving problems using differentiation. Yeah, and I've given us Thursday and Friday to be across these kinds of things, but with the idea that I probably won't have 2 lessons worth of work for you to give you a chance to revise over the stuff that we've done in this unit. So that's kind of the idea there. And on Monday is the rate of change test. Okay, so that's this Monday coming up. Alrighty, so really I've got some of us to do, and then I've got some work in the textbook. There's not a lot in the textbook, so I reckon I'll supplement it tomorrow with other problems, but it should be enough for today. So what we're going to do today is we are going to focus on going through a problem and seeing how to model it. Now, again, if you've done Maths Extended, I get that you're probably across this, but you haven't had me as a teacher. It doesn't hurt to have another voice going through this kind of stuff, but I might say things in a slightly different way, and that might be assistive for you. If you're feeling like there's nothing you can learn from me, exercise 5Q is where it's at. I want you to work your way through exercise 5Q. No judgment from me if you don't want to pay attention to me. So, optimization, well, any word problem at all, really, application problems. We are doing optimization problems, but I believe there's a really simple 4-step model for optimization, for any word problem, really. Number 1 is that often it is minimize this concept of the literacy part of an application problem. And that means that before you can tackle a problem, you need to understand what the problem is, and you need to understand what it's asking of you. If there are words that you don't understand or concepts that you don't understand, simple or big, then it's going to hamper your capacity to solve the problem in a meaningful way. So number 1, as you can see there, I've got understand the words. I know that sounds like a very babyish the way I've written that, but it really is exactly that. It talks about a coiled spring has a tension of, which is given by the function, and you really aren't too sure what the difference between a spring is and a coiled spring, then that's going to stuff you up, isn't it? Because you might not be answering the question you think you need to answer. Maybe it is irrelevant, but until you've sort of worked out the literacy part, then you don't know whether it's relevant or not. And then determine, what do I need to solve? Okay, and when I go through the example problem, you will see that writ large. Have you solved the problem, or have you answered the question? Then the next step is, when you have a word problem, is you have to come up with a model. Often a diagram will assist, as opposed to a drawing, or diagrams.
Is that always?
That says, oh, what happened to my A there?
Yeah.
I reckon I erased it by mistake.
Almost always.
Almost always. Almost always, a diagram will assist. And of course, what we're really trying to do is we're trying to take a problem and distill it into a mathematical function, so that we can use the function to interrogate it to solve the problem. So I would say, particularly in a mathematical context, you'll need to come up with a function. And usually the way you do that is by looking at the problem and identifying, oh my gosh, variables. That says variables. It might look like variable to you, but it's not variable, it's variables.
And
and this one,
it's not
oh, right. Picky, picky, picky. Variables and constraints. Okay? So the function will be created by considering variables, the things that you don't know or will need to figure out, and the constraints. And the constraints are what are the restrictions or what are the, it's often given as numbers or some sort of fact, which means that it's constrained. So if I said, very, very quickly, I'll just say this, but it comes out in the problem. If I said I need to create a rectangle whose length is twice as long as its width, and the perimeter has to be 25 centimetres, then the variable is the length and the width. And the constraint is the perimeter is 25 centimetres. Therefore, the length and the width will be constrained by the perimeter being 25 centimetres. Am I making sense there? Variables and constraints. I'm going to zoom out and you'll see the example, but I just want you to be able to see everything all at once at this point. So the third step is solve using techniques. So it might be that you need to use null factor law. You might need, there's a whole bunch of techniques you probably have to use if it's a complex problem. For an optimization problem, however, it's almost always going to involve calculus. Because remember, one of the results, well, given that calculus is the study of rate of change, and given from last lesson we know that when the rate of change is 0, the function will either have a maximum or a minimum at that point. Then we can put those facts together to solve an optimization problem. Because, and I didn't say this at the start, because it's one of those assumed knowledge things, optimization means finding a maximum value or a minimum value. That's what optimizing is, finding a maximum or a minimum. And step 4 is, did I answer the question? So you've got a solution, did I answer the question? And the other sort of related thing I should also say, you should also be doing is the answer reasonable? So you've got your rectangle, you're told that the length has to be twice as long as its width, you know it has to be 25 centimetres, and your answer is, well, if I make the width 94 centimetres, I'll be good. Then your answer is not reasonable, right? If one of your sides is actually longer than the whole perimeter, you've stuffed up somewhere. Okay? So that's what I'm talking about. Is the answer reasonable? Okay. Where do you think students tend to spend most of their time?
Solving.
Yeah, number 3. Step 3, isn't it? And often students will attempt to go straight to number 3. Okay? Now, it is true that from a technical perspective, you probably will spend a decent amount of time in step 3. But please do not discount step 1 and step 2. Okay? The more complex the problem is, the more this becomes an issue. If you rush into writing a model, but the model is rubbish because the model is based upon assumptions that you shouldn't have made or a misunderstanding of the question, it doesn't matter how good your mathematics is, your answer is still wrong, your model is still wrong, it's all just wrong. Okay? So do make sure you spend time with the literacy section and the modelling section so that when you do solve it, it's actually worthwhile. All right, so on slide 3, you can see an example. Is that really as big as that data projector gets? I just realised how small that is.
You can zoom in.
I feel like it's just like really teeny tiny, but it's probably the way it has to be.
Because of the light, maybe.
Well, I feel like it's because if I made it bigger, it would actually zoom out this way as well and hit that.
Surely it should be
If you
further
just
that
shift
way
it
a
and
bit.
zoom.
Put the projector's in the wrong spot.
If I shift it and zoom,
If you move it this way,
Yeah,
a little
on
towards the
mine,
right,
you
and then
can-
you zoom in using the zoom function on these ones. They usually have like one of those like clicky
If
things
you
that just
move the
it.
literal thing.
do you mean actually move the white space
The
there over to
projector.
the right?
Not saying if we move
You mean
the projector.
disconnect from the ceiling and put it over there?
No, can't you like turn it?
You mean twist it?
twist.
Oh, okay, yeah, you could do that, but then you have to deal with, what's it called? Turning, something like that, to make it all, no, keystoning. Because if you do it at an angle, it comes out trapezium shaped instead of rectangular shape. And then you have to keystone it. It's above my pay grade. We'll deal with it. It's okay. Is that too small down the back? Was that okay? Okay, cool. Okay, what am I complaining about? Here's the solution then. Now, here's the question. Sorry, I didn't have to go through that. So I'll go through it, even though you said you could read it. A sheet of metal, 24 centimetres by 20 centimetres, is to be used to make an open box. Squares of length x are cut out of each corner. Find the dimensions of the box. That will give a maximum volume. Yay! Excellent. Everyone understand every single word? Anyone got any questions over those words?
The finder, what does it do?
Here?
Yeah.
Dimensions? Good.
Dimensions.
Oh, dimensions, yeah. So the dimensions of a box is referring to
Height, width, length.
length, width, and height.
This is
Zoe, why is the word open important?
because you don't have a lid.
Good. Because if I did have a lid, the shape I'd have to make out of the metal would be more like a T shape, wouldn't it? So that it would have a lid as well. So that would radically change what the cutouts would be. Okay. So knowing that it's an open box is important. There are some things I'm going to take as granted that you understand what a sheet of metal is, a flat sheet of metal. Squares of length x. So again, it's not so much that you wouldn't understand it, but just make sure that we're conscious. We're cutting out squares. We're given the variable. We're not always, but in this case, we're given the variable. Cut out of each corner. That would make sense. So right now, I'm sort of imagining what it's going to look like in my head. And really, in practice, I'll probably start drawing a model as I'm reading it, and find the dimensions. And importantly, it has to be a maximum volume. It doesn't say make it as long as you can. It doesn't say make it as high as you can. It says make the volume as big as you can. So that's okay. So reading through, and by the way, this is not that complex, but often don't be afraid to read through a problem more than once. Read through it once for words. Is there any words I don't understand? Or has Richard written them really poorly, like dimensions? Okay. Secondly, now, what are the key things here? Now, what are the constraints, for example? Well, that the sheet of metal is 24 centimetres by 20 centimetres. I can't magically make it longer or shorter. There's a constraint. What else? What don't I know? I don't know what the length of x is. What do I have to find out? Well, I have to find out the volume, and most specifically, the maximum volume. Okay, great. How do I put it together? And then we're ready to go. So the solution, what I would probably do is I'd probably just draw the sheet of metal out, and I'd say, okay, what do I know from the problem? I know that it's 24 centimetres across, and I know that it's 20 centimetres in width. What else do I know? I'm told I have to cut out the x's here. So that's x and x, and I know they're all the same. I won't put them all in. And I don't know what those shapes are. Well, what else can I work out? What do I need to know? Well, I'll need to work out the volume. And the volume of a cuboid, of a rectangular prism, is given by
Length times
Length times breadth times height.
breadth or width times height. Yep. So length times width times height. Do I have the height? Now, this is where you need to use your imagination. If I folded that up, I can see what the height would be. Rose, what would it be?
X.
Awesome. What about, okay, it doesn't really matter which one I use for which, but I'm going to use, because it is longer, I'm going to use this for the length. So I can see, and I think you all could see that this would be the length. But I don't have a value for that yet.
But
Yeah.
what I haven't understand why we have a sheet
of metal,
Yes?
and then we talk about box and volume. Because
Okay.
you're cutting bits out of
So-
the corners and then you're folding it up and making.
If this is what a sheet of metal.
Right.
Yep. So what I've drawn here is effectively a net. Did you use that word to describe a flattened 3D shape?
Oh, that's cool.
Okay. I'm going to call it a net. So this is a net, and if I fold along the dotted line, well, not the dots, but if I fold along, I get the open box here. Okay, so I need to work out what that length is and then work out what this width is. And I can do that. That's all pretty reasonable, I think. I know that the total length is 24. So therefore this length here must be, okay, 24 minus 2x. Can you see that? There's an x there, there's an x there, so it's 24 minus 2x. Zoe A, do you want to give me the width?
You got 20 minus 2x.
Yeah.
Because it's the same thing, you're taking x's.
Same logic, just a different total length. So we've got length equals 24 minus 2x, and we've got width is equal to 20 minus 2x. Well, this is good. This is pretty much everything we need. Now, before I go on any further, I want to explain something to you. I've deliberately chosen a problem which I believe, which has not very nice numbers. That's on purpose. But what I'm not going to do is I'm not going to go through you watching me put stuff into calculators to figure out the numbers. I've worked it out beforehand, okay? But I wanted you to see that, it doesn't have to be simple numbers all the time or neat numbers. Okay, so just keep that in mind, that I'm going to make a few shortcuts just to make it a bit quicker. Okay, so now I can use these facts to get a function for my volume. And my volume is going to be length, 24 minus 2x times width, 20 minus 2x multiplied by the height, which is x. Okay? And I can expand this. I start by expanding these two and then multiply everything through by x. And I would get 480x minus 88x squared plus 4x cubed. Is that okay with everybody? I'm shortcutting, but I think everyone here has the skills to expand the two binomials and then multiply everything through by x. Yeah. I need to switch to the next page in a second, so I just want to make sure if there's any questions, ask now before I head off over to the next page. Right, so all of that gets us to the bottom of step 2. We've understood the question, we believe we've understood the question. We've diagrammed it out to help us understand what's involved. And then we've created a mathematical model, which is that v, it's a function which relies on x, v is given by 480x minus 88x squared plus 4x cubed. I started with 3 unknowns, length, width and height. I ended up with 1 unknown, which is just x. And this is really common in application problems, that you may have multiple variables, but the pathway to success is being able to express all the variables in terms of just one. In our case, x. So once we've done that, it's now a function. If it's got more than one variable, it's doable, but it's more difficult to solve. Alrighty. So now we're up to step 3, solving using techniques. And genuinely, as a budding mathematician, you can rely, you probably need to rely more on your notes, your theory, maybe even if it's an exam situation, your formula sheet or information booklet, so that you can start thinking, I wonder what tools would apply here. With practice, that wondering becomes a more certain, well, these are 3 tools that will help me. Okay? So obviously, when a maths teacher gets up and just explains it, it feels like it might be just devil work, but it's not, it's just practice. So what I know is that when it comes to an optimization problem, I need to find a maximum volume, and to find a maximum of a function, I know derivatives give it to me. Okay? So, as part of my of writing stuff down, I will very, very, very clearly articulate where I'm going at each stage. Not with huge sets of words, but just something which cues the reader into what I'm doing. So I start off by saying max volume at dv dx equals 0 for some x. I know that I will find a maximum for v, and v is volume, remember, when the derivative is equal to 0. So that's what I do. That's my tool. I've chosen to use that. Maybe it won't work. I know it does, but if it doesn't work, then you go back and say, what other tools have I got? Okay, so dv by dx, you might be ahead of me by now, is 480 minus 176x plus 12x squared. That's the derivative, and I'm going to set it equal to 0, one of the very rare times where I'll put two equal signs on the same line. Rose, is that your hand up or are you just thinking? Yeah, cool. Good so far? So I found the derivative, I've set it equal to 0. Now, the first thing I'm going to do is I'm going to try and simplify my numbers here. I can see that all three of them are even. So I know that there's a common factor of at least 2. And with a bit of experimentation, you'll be able to see that there's actually a common factor of 4 there. So when I've got an equation set equal to 0, dividing by a common factor, number factor, is really useful, because when you divide the other side, the 0 side, by a number, it's just still 0. So I'm going to divide by 4, and I get 120 minus 44x plus 3x squared is equal to 0. So I now have an equation, a quadratic, which I can then solve for x. Now, hot tip, to save us time, well, summary is, to solve from here, I could use completing the square. I could use null factor law by factorising, using the diamond method or something, or I could use a quadratic formula. Now, to save us time, I'll tell you now that solving by null factor law is no good because they're not integer numbers, the solutions. So you could go straight into using the quadratic formula, I think. So if you did the quadratic formula and used your calculator, because I don't really need exact answers for the measurement of x. So I'm going to summarise that by going by QF, by the quadratic formula, I can work out that x is equal to 3.62, or x is equal to 11.0. I'll do it properly. 11.0, three significant figures. It's 11.045. Now I will put it in, because really you don't need to do three significant figures until the last line. It's better if you don't use significant figures until the very end, so you don't have rounding errors. So I'll put the whole thing in. 3.62 and 11.045 is the approximate there. Okay, good so far? I've shortcutted, but quadratic formula would give it to, and a calculator, of course. Alrighty. So, we've got two values, 3.62 and 11.045. One of those, either of those could be a maximum. If you know what a cubic looks like, and unfortunately in this course you don't need to know, but a cubic either looks like this, and transformations will take it elsewhere, or a cubic will look like this. So you can see from this, either it has a point of inflection or it has a maximum and a minimum. And of course that could be reversed by a reflection. So it could be like that. So that could be the minimum, that could be the maximum. So either of those could be a maximum. One of them is a maximum, one of them is a minimum, and I don't know which one's which. Okay? There are plenty of tools that will allow you to work out whether it's a maximum or minimum. But the easiest way without drawing it would be to use what fact? Rows. Do you know? You don't have to know, but I'm wondering if you know. What's the fastest way for me to confirm that 3.62, to confirm which one is the maximum? I know? Okay.
Well, like
Yeah?
looking in the context of the problem.
No? No, we're dealing just with our function model here, Aaron.
Second derivative.
Second derivative test. We could have done the first derivative test, which is to look at the values of the gradient either side and see whether it's increasing or decreasing. But remember the second derivative test. If we take the second derivative and we can show that at that point the second derivative is positive or negative, then it shows us more about the graph. I'm speaking too much. Let me just do it and then you'll see what I mean. So, test for max minimum. So I take the second derivative. Do you remember that's how you write it? d2v dx squared. This is not foreign to everyone, is it? I didn't miss something in your work. You have done the second derivative, haven't you?
Yeah, we did.
Yeah, I thought so. Oh, Zoe, you were away for one lesson. I thought that was the one we did
at
it.
least one, if not two lessons, because I've been sick.
Yeah, I was sick for one lesson as well. But it's all on Google Classroom, so it probably looks a bit foreign to you.
Was it the same lesson we did first principles last week, or was
The
it
lesson after.
something after?
Yeah.
Not the Friday.
It's all on Google Classroom, okay? So you just check that out. In a nutshell, of course, Zoe, for your first hearing and for the rest of you, to remind you, the second derivative is just taking the derivative of the derivative. Okay, so there it is on the board. Get ahead of me. This will be interesting to see what you get. Okay, guys, who wrote down minus 44x plus 6x? Oops, minus 44 plus 6x. Really? You did? You're wrong. Sorry. You can't work from the simplified version. You have to work from the first line.
Frozen again, if you just
Oh, are you serious? It was doing so well. So the answer is, I'll fix it up in a second, no, it's not frozen, minus 176 plus 24x. Did you get that? Good one. Yeah. Okay, that's the second derivative. So Zoe, you're about to see how it works anyway. So basically...
Just quick question.
Yes.
Because I got minus 176 minus 24x, which is wrong because of the plus minus symbol. Where would I have gone wrong with keeping it as a minus instead of changing it? Wait, how do you get a plus on the? Where did I get a minus from?
Yeah, I think this is more of an answer for you.
Okay, sorry.
Especially if there's
I thought that was a system.
Yeah, you must have stuffed up earlier on. That's all. Okay. Go back and check. It should have been plus 12x squared, and you must have had a minus 12x squared.
Yeah. Okay.
Okay. So what I'm going to do now is I'm going to have a look at x equals 3.62. So that's a straight substitution, right? So d2v dx squared is how you say it. Don't ask me why it's not d squared x, but it's d2x dx squared. d2v dx squared is equal to, and again, calculator job, right? Negative 89.1. Now, don't want to go through the theory of this again, so I'm not going to. I'll just remind you that when it's negative, it means it's concave down.
So it's a maximum point.
Therefore, it's a maximum point. Yeah. Negative second derivative means concave down, which means it's positive. I think remembering the concave down bit is kind of important, because otherwise you'll go, oh, it's negative, therefore it's a minimum. It kind of has the same connotation, which is counterintuitive. at 11.04, what did I have? 045? At 11.045, I should have written x equals d to v dx squared is equal to 88. It's probably 88 point something, but let's write 88 down. It's positive, therefore a maximum. And again, sorry, a minimum. And again, just to fill you with Zoe, if the answer was 0, it's inconclusive. Might be an inflection, for example, but it might be something else. So that's when you go and do the first derivative test instead. I technically didn't have to do 11.045 because if I know one's a minimum, the other one has to be a maximum and vice versa. But I did both just for the sake of it. And also, if I ended up with both of them being maximums, I'd probably go, oh, I've stuffed up somewhere. So it's like a check on my own thinking, which is kind of good in exams when you don't have an answer booklet to look at. Okay, I'm going to pause there for a second. And I'm going to just get you to think about those values there that I got on slide 5, 3.62 and 11.045. In actual fact, I didn't have to test for 11.045 at all. Why not? I'm going to ask you, Lily, but I want other people to have a bit of thinking time first, and then I'll ask Lily. So just have a think. Why don't I cross out 11.045 even without thinking about it? Now, assuming Lily's correct, I'm going to go back here because she'll want this diagram to explain, I think. Okay, go.
When you cut out the corner bit, if its length is x and one side's only 20, if you cut out 11 from both sides, you're not going to have anything left.
Yeah.
What's the place?
It's a constraint, sorry?
I said we can see instead of the second derivative test about the context.
Yeah. But we still don't know that 3 is a maximum.
Yeah, that's right.
You could kind of cheat and say, oh, well, it's the only answer I've got left, so it must be right. But I'll talk further about that in a second. But if that's what you meant by context, then you're right that you can discount 11.045, but it doesn't mean 3 is the right answer.
But you can use 3 as the one that you check first, and if that's a maximum and you know it's a cubic, then you know that you're right.
Sort of. I'll explain what I mean in a second, but sort of. So does that make sense why there's a constraint there, right? So our constraint is now made real, that x must be less than, technically less than 10. So you'd really probably say less than or equal to 10. But practically less than 10. Is that okay? So that allows us to discount it, but we still need to work out it's a maximum. Now I want to explain that a little bit further because when I said that at 3.62 we have a maximum and at 11.045 we have a minimum, that's a little bit of cheat speak, isn't it? Because we don't actually call it a maximum. What do we call it? It starts with L, a something maximum.
Local.
A local maximum. Yeah? And that's a local minimum. So let's just say we worked out that that this was legitimate as well, the minimum. For all we know, for all possible values from 0, let's just say it was up to 15, for example, it might be that the function goes like that. So in which case, that would be the maximum. That's a local maximum, but the endpoint is an actual global maximum that they're called. And that's why context doesn't give us everything in that regard. And even better, if we found out that the value was a minimum, that would almost guarantee us, because it was like this, that would almost guarantee us that this, if this is the only point, the only local minimum, then it almost guarantees us that we should be looking at the endpoints. I'm just using this as a for instance. If these were the actual constraints, that it can't be any less than 2 and it's going to be less than 15, then we should work out these values as well to see whether they're a maximum volume. Okay? 9 times out of 10 though, what I've got here is legit. the local maximum is almost always the global maximum as well. But it would be wrong of me to just not say that to you, because we're here for more than just exams. We're here to understand the whole thing. Yeah.
In a question like this, let's say that we use our GDC and we graph it out using that, and we see that there's a point that's above the local maximum. And would we say that particular point is the maximum value of x?
You would say, yes, you would say that would be global maximum. So
Value of
the
x.
turning point is a local maximum. So you would say, but at x equals,
So when
but at x equals 24, so global maximum at x equals 3.4, global max at x equals 14, whatever it is, and that would be your answer. But you have to prove that it's an appropriate answer. But yeah.
So then instead of saying your gradient's equal to 0, then you just say your gradient's equal to 14.
You don't need, it wouldn't be a gradient, that would be your value of x, wouldn't it?
Okay.
Yeah.
Yeah.
So 11.045 is actually impossible. 3.62 is a pretty good maximum. So we're done. Correct?
No.
Thank you. Why aren't we done?
You need to find the volume and the max and the length of it.
I would probably work out the volume maybe. No, I wouldn't. If I was in a test, I wouldn't, because it hasn't asked me to.
But it says find the dimensions.
It does say find the dimensions. It does say find the dimensions. So I wouldn't waste, probably if this wasn't a test, I'd probably just do it anyway. But in a test or an exam, I wouldn't waste time if it doesn't say to. I would just go, therefore, dimensions are, and then I'd just calculate them, right? So you're just going to get them from me, but you could use a calculator for this. And that is the answer. Again, frequently students will say, but I found a value for x, and therefore that's the answer. But it's not. The answer is to the question. The question was, what are the dimensions? Okay? Really important. Right, you've got about 15 minutes left in this lesson to make a start on 5Q, but I just wanted to briefly touch base that you can, of course, use your GDC if you have it available to you to work out these things yourself. The trick is that you still need to really work out the formula for yourself, that the GDC won't do that much magic for you. But once you've got it, you can then use your GDC to go further. So if I just add a new page, and I'm going to add a graphs page, I don't even have to expand it. I can just say, well, I can see that it's 24 minus 2x multiplied by 20 minus 2x multiplied by x. Press return. That gives me this rather large kind of thing because the volume is quite big. And so I can zoom out, if I can remember how. Menu, Windows Zoom. There is a zoom button, but I tend to use Windows settings as soon as I can. For example, I know that x can't be negative, and so I might just make it -1. And I know that x has a maximum of 10 because of what we said before, but if you don't remember that, it's a bit tricky. But I'll go 12, so it's a little bit further on, makes me feel better. And then I choose a y minimum and a y max. Now remember, y is actually the volume. So I'll just leave it with a really tiny value like that. And I know the volume's going to have to be pretty big with numbers like that. So I'm going to just try 500, and if that doesn't work, I'll go back. And although this requires a little bit more work to get it working properly, still not enough.
774.
Thank you. But imagine you didn't know. I don't mind doing this by hand, even though it might take you a little bit longer, because every time I do this manually, I get a bit of a better feel for what's happening in the function. I think it's much more controlled than just clicking on a zoom button. I really do. And there we go. And I end up with a much nicer looking graph. So you can see that I've got it going from 0 down to 10, I'm guessing. And I can see very clearly that there's a local maximum here and a global maximum because it's gone down again. Yay. And after that point, I know it doesn't matter. Even if the graph does go up again, it doesn't matter because this is my constraint. So then I can use menu, analyze graph, and there's a maximum button there. And that will just give you the biggest value across whatever you select. I'll show you what I mean by that, but then I'll go to the actual answer. If I click here to here, it's given me the maximum there for that range, i.e. it was obviously that point. So it doesn't necessarily mean the turning point. It just means the biggest value in that range that you select. But now I'll do the real one. So menu, analyze graph, maximum, go to the left of the turning point, go to the right of the turning point, and there's my value there to 3 significant figures, 3.62. So that's how you use your GDC to get that point. And please don't be afraid to use your GDC if it's in the calculator section. It's what it's for, just so you don't get slowed down. But keep track of how many marks a question is worth. So if it says find the maximum volume and you say by GDC x equals 3.62, and that's all you do, then it's worth 4 marks. You'll probably get 1 out of 4 for that. Okay, so you need to use the mark scheme or the marks as a guide to how much explanation you need to put with it. Okay, now I promise I will shut up, other than to show you where you're headed, and I'll put it into this thing in a second because I haven't updated it like a silly boy. So we're looking at exercise 5Q, sorry. Just go to the table of contents. I hate this online book so much. Can't do nothing. Here we go. So it is page 264. Thank you, whoever said that. And it's exercise 5Q. You've been given the structure. It's up to you now to apply that structure to lots of different problems to get familiar with it. So you've got the rest of this lesson, homework tonight, and our lesson tomorrow to do as much as you can, plus revising for the test on Monday.
So is tomorrow purely a revision?
What day is it?
Well, to be precise, I'm just going to